Don't worry about it. Awesome. Okay, I'm going to start, everyone. I think everything's shared. So
lemonade, some extra cups, and all that.
awesome.
For people.
Awesome. Hi, everyone. As you know, I'm Brando. So today I'm going to explain to you one of the papers that is under submission, right? Clear. And part of this work was accepted as a workshop for data-centric machine learning here this year for Hawaii ICML. So that the title of the paper is rather long, but hopefully it's a good title. It's called Beyond Scale, the diversity coefficient as a data quality metric demonstrates LLMs are pre-trained on formally diverse data. Work by me, Alicia, Sudarsan, and Professor Cuello. Yeah, and any questions, feel free to ask me. So now these are the contributors. Here are cool pictures of us. Awesome. So the introduction. So the main motivation for this work is that there's too much focus on, according to, I guess, what I'm observing is that a lot of focus is on scale, raw scale. LLMs are increasing in size, the data, both the models and the data. And I'm proposing to move beyond scale and to measure what quality and coverage means. So this work, we want to measure the effective number of counts and therefore counts of tasks. So we try to measure how many tasks are intrinsically in the data set through a diversity score that we are proposing and that has been validated in previous work by me and others. It tries to compute the number of tasks and therefore abilities. So it's a formal quantitative, hopefully well-motivated diversity metric. And eventually, let's see, eventually we also want to see how that metric correlates with like downstream performance. And the main motivation is that data drives, according to my hypothesis, drives everything. This is something I hypothesized since 2019 before LLM hype, if you see like some of my previous work. So diverse general data hopefully leads to diverse general skills, which is, I guess, what people call AGI, general. Yeah. Anyway, that's the small introduction. So I just want to, since the talk just started, I feel like our attention is the sharpest, and we want to maybe learn what exactly I contributed so that if you don't remember anything else, you remember this slide. So this is the slide to remember. So the contributions, an attempt to do a paradigm shift away from scale to diversity, an aspect of data quality. So we propose a formal diversity metric that you can compute. It approximates the effective number of effective number of tasks through this metric that we call the diversity coefficient. The main contribution is that we test that the diversity coefficient behaves as expected on NLP data with LLMs. Therefore, it is sort of like a valid diversity score. So we propose a diversity score and we validate it first, that it behaves nicely so that it actually measures diversity. We do this through different things. I'm gonna outline the three things I wrote here. Is that if the number of latent concepts in a data set increases, we expect the diversity score to increase, and we see that. We also see that if your, for example, tokenizer increases in vocabulary size, then you have more ways to express a single sentence. So we would also expect that if you increase the vocabulary size, the diversity to increase, or at least the diversity coefficient, I mean. The more data sets we concatenate, the more diverse the data set is. We also justify it through, like, if we knew the ground truth distributions, does the ground truth distribution diversity correlate with our score? So if you have a data set that has been created with multiple distributions and you add more distributions, therefore, like the ground truth diversity, like in a synthetic setting, does our score sort of correlate with that? So those are like the three ways we try to justify that this diversity score is valid. Then we go and show that this diversity score is high when we expect it to be high for open LLM data sets. We also compute some sort of well-motivated theoretical lower and upper bound of it. I guess that is like the main contributions. And we believe that we haven't tested it on multimodal stuff, but the diversity coefficient works on vision and other work that we have. And as long as you have a model to embed data, you can use this metric. Any questions? Yeah, awesome. Everyone can recite the contributions. Okay, just kidding. Ready? Okay, so let's motivate what formal diversity is. And the diversity should measure the effective number of tasks, abilities, concepts that goes beyond scale that is intrinsic to the data set. So for example, if you have task 1 and task 2, they're natural images. So the average distance between tasks would be low. So that's what the diversity coefficient should measure in this case. And in this case, the diversity should be high if you have like natural images compared to visual concepts that are handwritten, and that should lead to high diversity. So this is more or less what the diversity should be. It should measure beyond just if you have more and more labels, and they're all like in this type of data, then the diversity coefficient shouldn't increase too much. But if you start adding concepts in a way where the concepts are different, it should increase more. So the point that I really try to make there is that a lot of times people count combinatorially as you add more concepts, and then they say like, oh, you have like 1 billion concepts in here, but then you measure it with this score, and it actually isn't as diverse as people think. So that is more or less like the idea. Just increasing more concepts blindly doesn't always increase your diversity. Yibo, our Yibo, always asking good questions.
Yeah, so I'm just wondering, like, how do you think of this diversity versus for the complexity of the like all of the tasks? So like, are they kind of equivalent in some sense?
Great question. That's a good question. What is a good answer to that? I don't think they're equivalent. Yeah, they are related. The way we define diversity is by embedding tasks, and that gives us vectors, and then we compute the cosine distance. So we explicitly, and that is inspired by previous work, task2vec. Task2vec does that to sort of remove the complexity issue actually entirely from that metric. And when they want to consider the complexity, they use a different way to measure distances between tasks. So they don't use the cosine distance. So the answer is, I guess the more coverage, it can be harder, but not always, because you can also add easy tasks. So I think the answer is sort of nuanced. That's basically what I'm trying to say. Yeah. So I don't know if that helps.
Yeah, sure. So then I'm kind of trying to think of like examples where, for example, it has high diversity but low complexity, or like high complexity but low diversity.
Yeah. So okay. So let's consider this task, for example. You have a bunch of Gaussians distributions, and the diversity increases because you add more and more Gaussians. But as you add more and more Gaussians, maybe there's more and more intersection between the Gaussians, so it's actually harder to distinguish between them. So the diversity there increases by a lot. Let's see. Yeah, I would have to think. I'm just sort of thinking about it on the spot because I wasn't prepared for this question. We do have some sort of experiment like this, but let me think. Yeah, maybe let's take it offline so I can give you a good answer. Yeah. But it's a good question, and Gaussian intersections is something we explored, and it's sort of interesting in this direction. Yeah, thank you for the question. Yeah.
Can I have a question?
Yeah.
So exactly. why is contest? Like maybe just my lack of background, but it seems like you just have a bunch of image, and task to me implies some sort of decision process that you're gonna do something with it, or is it implicit, or I just missing something? It seems like you define like a data distribution, like there's a like handwritten thing and there's a natural image.
Yeah.
Why is it task?
Yeah, I think for this, the reason I chose this slide for two reasons. One, I already had this slide written, and it was, I think, nice. But in this talk, I'm only going to focus on NLP data sets. It was more to give you a conceptual understanding of what we're talking about. Maybe it wasn't, maybe for future slides, I will just give you like a one that is in the modality that is like in question for the paper. So that is that what is maybe confusing you, Zan?
Well,
I'm trying to also understand the
thinking-
question.
I'm just thinking like the task, you mean like a prediction task, or like a generated task, or like a
Got it.
like
Yeah.
classification,
So ignore this for a second.
right.
Like the LLM dataset experiments that we're doing is, can you just standard perplexity? You're pre-trained on something, and how well do you do on the perplexity on a different evaluation? So that is, I guess, the task.
Okay.
Yeah. Does that help?
The complexity on different tasks.
Cross entropy. Yeah.
Right.
Yeah. You have some training set that you train on, and you have a separate test set that you evaluate on using cross entropy or perplexity.
Right. Okay.
Yeah, that's it. Tim.
I was curious, how does the definition of diversity interface with the size of the task in terms of the data? So you could also have a very long tail distribution of tasks where 100 tasks where 80 of them only account for 10% of the data sets. Does the definition take that into account?
It can. I think right now the way we do it is we in the paper we do have like data mixtures, so that so the definition can take it into account is the short answer. You basically you have a data mixture, and you weight the probability of sampling a batch from that data set differently, or mixing, or the probability that when you interleave the examples reflects some data mixture. So yeah, you can play with that. Right now, I suppose it's like a separate hyperparameter you would like specify. Yeah, it is interesting how to find those numbers. I suppose one of the main reasons I didn't really explore it is also hard to do everything at once, but Doremi already has something like that. And I think Doremi is more guided in terms of like producing the best model, is my intuition. And our work is more scientifically, curiously motivated. Like, how does the diversity, given some sort of reasonable maybe definition and hyperparameter settings, or things that are done in practice, that reflect things that are done in practice, affect the test performance? I think that is more or less the way we've been thinking about it. Awesome. Okay, so now I'm going to go sort of into the details for the background and motivate as much as I can, and hopefully convince you that the choices we made make sense. So this is the background. So we need an embedding for a task or a batch or a data set. So I will explain the difference between those in a bit. But for now, think that we are going to embed data. And the way we embed the data to represent the task is using the diagonal of the Fisher information matrix. So this is the Fisher information matrix. You compute the gradient of some sort of your model, and you compute the outer product of the gradients. We use, because it's LLMs in this data, we do and natural language processing. It's conditioned in a normal way that next token prediction would be. So then we extract the diagonal of this, and that is what we call like the Fisher, like the task-to-vec embedding of some batch of data. Let's see. So one of the motivations to use the Fisher information instead of like activations is that the Fisher information sort of tries to, like, once you fitted the parameters to your data well, like it tries to sort of, at least in linear and more traditional settings, it tries to sort of give you like a Gaussian around what the generative parameters are. So I think that is why previous work, the original task-to-vec, chose this metric, because we're trying to approximate some unique fingerprint for the generative parameters. That is more or less the intuition. Sort of hand wavy, but I think like the best justification for this is like the empirical experiments to how it correlates to intuitive notions of task and diversity. And that's how I think it's a better motivation, but I always seek to find intuitions anyway. Does that sort of make sense? I think it's better to move on and show you like why task-to-vec works. So these are like two reasons we think task-to-vec are good embeddings of data or batches of data. One is like the original work by task-to-vec, where they show that similar concepts cluster together. So birds cluster in green, mammals cluster in purple, plants cluster in brown. So yeah, visual concepts cluster. That's work by task-to-vec, the original author. That's not our work. Then we do a similar sanity check, but in terms of NLP data. So some of the things we do is that when we compare data sampled from the same, when we sample batches from data from the same distribution, we would expect that to be lower than when you sample data from different data sets. And that's what this is showing. So if you sample data from, say, C4, like Common Crawl versus Wikipedia, and you compare, when you cross-compare it, that's higher than when you compare Wikipedia text to Wikipedia text, and that's lower than the cross-comparison. So that is like, say in one slide, like the summary of all the experiments to show that task-to-vec behaves more or less the way we would want it to behave. Does that sort of help? So similar data sets have smaller task-to-vec distances than different data sets.
So the figure on the right is
Yes.
I embed combinations of tests. And I look for some notion of distance between one task and another, or one data set and another one, aggregated over, I guess, labels possibly.
Something like that, yeah. So more precisely, you have a data set C4, you sample a batch. Another data set, WT103, you sample another batch. You embed those separate batches that aren't mixed. You compare how far they are using the cosine distance and the task-to-vec embedding. And then you do this a lot of times and take the average. And that's what this number is. That's why you have like a whisker plot around like the variance. And you repeat that but using the same data set twice. Does that make sense, Professor?
Yeah.
Awesome.
Yeah,
Sorry, I think so.
No. I was reading the question, but go ahead.
Yeah, so I guess to clarify, you have this task-to-vec model trained using Fisher information, like maximize informativeness of like, since you're using the diagonal, it's like of each parameter, like for the MLE estimate on a given data. So we have the model, we do this, and then it's like cosine similarity distance or something.
Yes. Yeah.
That's interesting.
Yeah, the way you do it is you fix a model, then you fit it to the current batch a little bit, then you try to then you compute. Once you fit it, the last layer in this case, to the current two batches,
Yeah.
you have a better set of parameters for the current task.
Yeah.
And then you'd compute the gradient, the Fisher information, and get the diagonal.
Okay.
Yeah, and I have a slide about that actually, but I think we haven't. Sometimes it's hard to decide exactly what's the best order of all the slides.
Yeah, that makes sense. So then like you want the elements of the diagonal to be like independent, like your model is in some way like learning as much of it as it can from this data. I mean, like each feature is like maximally informative for like describing the data.
Yeah. So is the question why the diagonal? Part of
Yeah.
it is computationally, actually.
Yeah.
So it might be imperfect. It would have been better to use maybe the whole Fisher information matrix.
Yeah.
But
Well,
I'm sort of using what they proposed because it's also being tested. So the more things we start changing, the more things it could break in unexpected ways. Yeah.
Yeah, I guess maybe a broader point is like, since we're assuming the underlying model has like has some good implicit measure of like diversity here before doing this Fisher thing, like is perplexity in and of itself like not a good measure here? Because you could say if you have a language model trained on enough of the internet and like you measure perplexity over like a given data set, if it's low, then it's like that's not a very diverse data set. If it's high, it should be very diverse.
Sorry, I'm not sure I understood the question. Is the question what type of backbone to use?
Well, I guess like the question is like practically like did you do ablations which is like using perplexity as like a measure of diversity from like a larger model? And two, like, do you feel like, yeah, if the large model is like has seen enough data, is using its perplexity like spiritually the same as this like diversity measure?
I'm not sure. I didn't, but I think I also don't understand the question, so that's why I don't not sure what to.
Yeah, I guess I don't
Let's
wanna
ask.
derail things.
Let's chat later. Yeah, I'm happy to help. I just don't know
Yeah.
what to
If you have
say.
a precise definition of the sort of pairwise cross-test thing, I think that will help.
This one, this slide,
This is for
or
yes.
maybe once I get to that slide, maybe we can return to the question.
Sure.
If you go back to the formula, this might help you. It's just a comment, and I apologize if it's intruding, but the derivative of this is it's like p derivative divided by p, right? And then when we do this outer product and only look at the diagonal, that's each entry of the inner product.
Yeah.
So like if you end up summing that, it's just the inner product, not the outer product.
Yeah, it is like I forget the word for it.
Sorry, what's your comment?
It's like the square.
It's like another interpretation.
Yeah.
If, like you're confused why it's like.
No, that makes sense. I guess the question is like we're using a
The
model.
cross, yeah.
This model has some notion of information about the world. We're measuring like how well can this model predict this data? And like because it's seen a lot, like if it cannot predict it very well, if there's like high variance in this like in the diagonal here, then in some sense like that feels like a high diversity thing. And so I'm just wondering if like perplexity is a simple measure here, but that's more of like a philosophical point we should.
Yeah, I'm not sure. Yeah.
So, well, maybe we should go a little bit more and see if you answer the question.
Yeah.
There is a question on Zoom, which is asking about.
Yeah. I haven't, Nikhil, I haven't explained that part. Yeah, I'll explain what task is in a second. I think like just since it was asked real quick, I think the way I think about task is just sort of like the generative distribution, given like for example, if you generate arithmetic sequences from arithmetic, that's a task, or you get batches from a specific data set, that is a mixture of tasks. So that's more or less how I think about what task means. So the shortcut I use in my head is the data set, the collection of data points is like a snapshot of the task or tasks.
Sure,
Yeah.
but is the analogy between data set and concept or task a bit strong, given what you just said, which is like a data set you're thinking of as a collection of different tasks?
Yeah, I think I don't think let me think.
So you can't really isolate a task per se. You can
Yeah,
isolate,
sometimes
you
you
get a
can,
data
yeah.
set and you're getting a collection of whatever the data set
Yeah,
is capturing.
and I think that's more of a weakness. Well, I don't know. That is also the name of previous work.
Sure.
Yeah. So I would maybe call it data to back.
Sure.
But I guess
for them, the task was each data set was a different task.
Yeah.
Whereas there's a stronger notion of, or more
general.
Maybe general notion that you're pushing for here.
Yeah, I think so.
Okay.
Yeah, I guess like and once the definition of diversity, I bring it up, is like we just want to get a feel how different the data that you sample, how different the batches of data that you sample from your data set is on average. That is like exactly what the metric is. And let's see if it comes up. Okay, well, okay, I'll skip the slide, but it's sort of showing that ground truth diversity correlates with task to vec diversity, previous work in our lab too. I'll just skip it for now, but let's just jump into the definition of the diversity coefficient, which is say that you have, I'm just gonna move this so I can see. So the definition of the diversity coefficient. So the diversity coefficient should measure the effective number of tasks beyond scale, a soft count, so the number of tasks. It's more or less an approximation to, I guess, an indicator, soft indicator. So we use the cosine distance of task to vec embeddings, because that's what's been tested in previous work. Beyond scale, one simple thing to try is to aggregate using averages. Plus, we're also like these self counts is also going a little bit beyond scale because we're not counting hard. Like if you add a new concept, we don't say +1, right? We don't say that's an additional. That doesn't make your data set more diverse in a exactly incremental way because we take into account everything else that has been added to the data set. That is sort of like what I mean beyond scale. And in this definition, if D has many data sets, then the data is interleaved, mixed, or there's a union. There's like the sequences, the examples have some sort of probability to come from the mixture of the different data sets in D. So that is, this diversity coefficient takes into account like interleaving and for mixing of the data. And here's just some reminders of the notation. Does this?
Right. So on this definition, right?
Yeah, yes.
So I think the claim then is in order to compute diversity, I need to first sample 2 subsets of data sets, or at least 2 B1, B2, and to fit a model on each one of B1 and B2. Right. Compute the diagonal of the Fisher information matrix of the fit model, and then do this multiple times to get a full distribution. Okay, and then average over. And
maybe we should present this slide like much sooner, but
I think before you talk about the results, you should consider the definition, because I think part of the confusion was the pictures with the, I guess what it's called, the violin plots came before the definition of what you were using to compute that. Using.
Okay, yeah. I'll make a note of that. Good point. Yes. Yeah. Maybe the reason that came in early was because I was trying to show that task2vec by itself is already sort of justified. That's why, and there was like some sort of cyclic issue, and I didn't know how to solve it. One way to solve it would have been to not include my results and just justify with task2vec, and then justify my results again as a like recollection. Yeah, so maybe I'll do that next time. But yeah, thank you.
Yeah, can I go back to the last one?
Yes. No. Okay, yes.
I have to go, but I agree with Sandy's comment that explained the question.
Yeah, so I'm just wondering like the role of the batch size here. So for example, intuitively, it seems that with a smaller batch size, then this diversity coefficient will be greater, and then with a larger batch size, this coefficient will be smaller.
Yes, that's true. We do this experiment, but I think, yeah, great question. Actually, it's in my appendix. I don't think I don't think it's in the paper. We also have it in the appendix. I think the main way we like solve the problem of the batch size is like, as long as your batch size is sufficiently large, so that and consistent across your experiments, that's what matters. Like if you choose a batch size of 2, then it's hard to get a good estimate of the Fisher information. But if your batch size is like 1,000, then your GPU memory will go out of bounds. So for us, we chose, 512 is like the batch size, which is, I guess, big-ish. So so that is the role of the batch size.
So then can I say that ideally we want to use the whole data set?
Yeah, and good question. Yes and no. There's always trade-offs. If you use the whole data set, you're gonna have a single embedding for the whole thing.
Yeah.
You get no confidence intervals on like how diverse the data is during training. So you will probably get the most accurate difference, but then then you lose this notion of variance, because it's hard to, well, if you know, actually, I've been thinking about this, but if you know how to compute variances with respect to batch size through a very complicated nonlinear function, let me know. Then I can compute confidence intervals on some other things I want to do. But my solution right now is make the batch size big enough so that it fits in memory and report normal confidence intervals. But good question, subtle points. So yes, this slide. Basically, this just outlines the process of how we compute the diversity coefficient. So we sample from some fixed data set or a mixture of data sets. We sample some batch. We have some model, in this case GPT-2. We fine-tune only the last layer. The reason we fine-tune it is because task2vec does that, and that's like the results that we know work. So before changing more things, we didn't want to like break it. So we just sort of respected what they did for now. We fine-tune the last layer, then we compute the Fisher information diagonal. Then we have task2vec embeddings that lie on some high dimensional space, and we compute like the average cosine distance between them. And then we repeat this whole process a bunch of times so that we get the confidence intervals with respect to how things are done in practice. Yeah. Cool. Okay, so now I'll introduce like some other notions of diversity. The motivation is we want to show that our results hold even when you define it a little differently. Also, it's a useful, the other definitions will be useful for other things I want to do in this talk. So another way to define diversity is what I call cross diversity. And instead of just mixing everything, you actually just have them set back. You don't mix the examples. So that is what I call cross diversity. So now B1 only has data from D1, B2 only has data from D2, and then you compute the distance. These numbers tend to be higher than when things are mixed, but it's just a different way to compute the number of tasks without mixing. Yeah, so the effective difference of tasks abilities that go beyond scale when comparing two different data sets. The rest of the things are the same. The main difference is the no interleaving, the same notation. Yeah. Yeah. Any questions?
How would you define this if you had more than two data sets?
Yeah. So that is actually, when I made the slide, I noticed I missed that expectation for explaining it when we want that case. But you just sample different data sets according to your mixture. Yeah, the great question. That is one way to do it. I'm not saying it's the only or best way. Yeah. Okay. Okay, so why two definitions of diversity? Like I said, if we have different measures of diversity and it helps us conclude that the diversity is high, then there's like more ways to understand the role of the metric or the stick that you're using to conclude your results. Also, cross diversity sort of computes also the distances between two data sets or the average distances between batches. So for other experiments that we show in this work, you can define alignment using this metric, and then this metric maybe can be used to choose how two data sets are aligned and therefore understand further the role of data, for example, for fine-tuning. That is also what we define cross diversity. So I'm putting just the two definitions in one slide. One data set, the data sets have been separated explicitly. Okay, now just to make all the equations in one place. So the data alignment is 1 minus the diversity coefficient because of the cosine distance. Maybe there's like a different way to define alignment if the distance is different, but this is how we define alignment. And this basically tries to measure how close two data sets are, hopefully to help us choose better examples for fine-tuning, for conditioning and context learning, if you have a problem in mind that you want to solve. And I'm trying to see if I can use this to solve auto-formalization, because that's like the task I like, which is about mathematics and translating natural language to formal language. Any questions? Should I move on? Yeah, you'll see some experiments with all of these things soon. Okay, now all the metrics in one place. So the hypotheses, I guess, are diversity leads to diverse general intelligence, equation 1 and 2. Alignment to domain-specific intelligence, equation 3. Yeah, that's like the summary of all the metrics we propose.
So I think we need more thinking on 1 versus 2 and sort of why you might want either one.
Yeah.
It makes sense that you'd have a smaller number in general for the first one, given that you're mixing.
Yeah.
I don't know. I don't have a good justification.
Yeah. I think like maybe, one justification. I'm not saying this is correct or the way to do it, and I've been curious to actually, is that the main reason we define one is that that's how models are trained in practice. As far as I know, there is no single model, no model that's ever been trained this way. So that could be interesting to see like the role of different ways of training.
What is trained this way? What would that mean?
Yeah, so you sample, so you have a data mixture, say only two data sets, D1 and D2. You sample data from only one data set and then do a gradient step. Then on the next step, you have the probability of sampling from either data set. Say this time you sample from B2 and then you train your model with a gradient from this data set, then you continue. Rather than always having data from both things. Maybe this one's better, maybe this one's better, I'm not sure, but we choose this one because models are trained this way.
Okay. I'm a little bit
Confused.
because the second one I interpreted to mean, I guess B1 is only from data set one.
Yes, that's
And
correct.
your Fisher information matrix is only from data set one.
Yes.
So you train all the way to, I guess, to whenever you want to compute the Fisher information matrix. I guess it could be one gradient, but I'm assuming you're doing more than, well, it depends on the setting. Okay, I see where you're coming from.
No, I understand the question.
The messiness.
Can I
Sure.
interrupt real quick? So the
The
question,
interpolation thing confused me the way you
Yeah.
expressed it.
my apologies. What I mean is that my comment meant to say how models are trained in practice, irrespective to my work. So if you ignore my work just completely, people when they have two data sets, they specify the probability of mixing the sequences from each data set.
Mhm.
So yeah, so that's it. And I'm trying to see, I'm trying to mimic the different ways that you could sample data sets to define different diversity coefficients. But
It's a little bit unclear why it has to be very tight to the training process,
yeah,
given that
no,
this is measuring.
right, and maybe it doesn't have to. Yeah, and I guess part of that's why I think I try to justify it here is that if why two definitions? If our results sort of align, like are
Sure.
consistent across different ways to measure diversity, maybe it just makes our experiments a little bit more robust. Maybe one way to interpret it. What is the best way to compute diversity? Not sure. I would have to think about it. Yeah, that's a good question.
So maybe there's overloading. So like if you looked at these literally, it would seem like diversity, if D1 equal D2, then like the definition would collapse to the first one. But
That's true.
But okay, so it's not clear though, because you have to fine tune your model first in order to compute the Fisher information. So if you sample from one distribution to do that fine tuning, right, that's different than sampling from like a mixture, right? So like perhaps like f of B1 in that first equation is different than the one in the second equation. And so if you like added an extra symbol, it would maybe clarify that like these are completely distinct.
Do you mean just sort of call either the F or the diversity something else?
Well, like specify like under which condition it was fine-tuned. So like with respect to like which distribution. So like this isn't enough information to know which distribution it was fine-tuned on, right? Because like to compute the Fisher information according to the previous diagram, you need to fine-tune the last layer of the model. So then that's with respect to some distribution.
Yeah, to some batch, yeah.
Right.
To some batch, yeah.
Yeah, so then like the F of B1 is underspecified without telling you like with respect to which distribution was the Fisher information fine-tuned.
It was fine-tuned with respect to B1.
It's just
that's the
B1.
definition. So B1, I guess B1 is taking the role of sort of telling you what the data distribution is, and then F is like dependent on the B1 that you chose.
F is just dependent on B1. Okay.
So B1 can be sampled in a few different ways, right? Either from the mixture or separately just from dataset 1 or dataset 2, I guess. And depending on how you choose to do your sampling, F is fully defined.
Pending also. No, like is it defined just by F of B1?
Yes. Well,
Because
I mean,
like if it
B1
depends on anything else, you need to just add.
I don't see what else it depends on.
No, okay, as long as that's true, then what I say then is true. And like if D1 equals D2, then these are equivalent.
That's correct.
I think we're all in agreement. Yeah, awesome. So yeah, so just quick recall of the contribution so that maybe the results make sense. So we validate tests that that we basically try to validate if the diversity coefficient actually is a valid diversity metric. Therefore, we check if it behaves as expected with NLP data sets, with LLMs. That is like how we check if the diversity metric is a valid diversity metric. And therefore, the results with respect to that, if the latent concepts, if we have more latent concepts, then the diversity should increase. If the vocabulary increases, then the diversity should increase. If we get more data sets together, then the diversity should increase. So we do all these checks. And then to finalize that, we want to also show that the diversity is high for data that is actually used to train models, open source models. So for that, we define well-motivated ways to upper and lower bound it so that we see what should be the theoretical maximum and minimum of the diversity coefficient and show that how big it is or small with respect to those. And I guess the last one from previous work, if it correlates with ground truth diversity. Yeah, so those are the main results. And this is the first plot. So result. So the diversity coefficient increases as the latent concepts increase. In this setting, we use previous work from Stanford. Michael is the first author. The idea is that they have a synthetic NLP dataset called GINC, generative in context. That's what GINC stands for. There's one hidden Markov model for one synthetic NLP concept. Then you get lots of hidden Markov models, and you have a mixture of Markov models that is like the collection of concepts in a data set. And then the data point is a sequence generated from this HMM, this hidden Markov model. And as we have more latent concepts, the diversity coefficient increases. And this is what the experiments that we ran. It saturates at some point, maybe because the data sets are synthetic. Any questions? Does that sort of make sense? Great. Now, similar on GINC, but this time we check the role of the vocabulary size. So the hypothesis is that as the vocabulary size increases, the diversity coefficient should increase because there's more diversity in the sequence. There's more information, there's just more ways to arrange sequences now because of the vocabulary size increasing. So I guess that predicts some sort of exponential-ish growth in the diversity, maybe. That was, I guess, how we explained the result, that this trend, when we saw it sort of jump up, we attributed it to that. And yeah, that is this result. Does that make sense? Okay, so now the next result is that diversity coefficient should increase as we concatenate more data sets. So basically we have a list of data sets, and as we add more data sets to the mixture, the diversity coefficient should increase. This plot shows it just for 2 because it's the most conceptually simple way to explain it. In this one, we also have pairs, and this dotted line shows all the points that are single data sets, and when they're mixed is above. So these are all basically the mixtures. I guess these 2 aren't. And these, I can comment on these if we want to talk about them, but the diversity increases there's a final slide that talks about the nuances. But the idea is that if the data sets are already similar, like NIH and PubMed, if you add data sets that are already similar, the diversity does increase, but it doesn't increase as much because the data sets are already similar. So that's what's going on there. When we have 5 data sets, that's the biggest increase. So concatenation increases the diversity. Same plot, but with just pairwise. Makes sense? Pairwise concatenations. Now, this is the plot where we have, I guess, Sammy and Zach were talking about like this equivalence when you have like D1 and D1 plugged into the diversity coefficient. So that's why we have lots of same as left. And when it's not the same as left, we computed the numbers again. On this one is like the normal diversity coefficient when the sequences are mixed. And this one is the cross diversity when we know exactly that the batch came separately from separate data sets. And we also have the theoretical lower and upper bound. So the lower bound is, say that we have sampled given the vocabulary, always sample the same token, and then compute how diverse that is across all the vocabulary, across the entire vocabulary. And that's not very diverse as you would expect. So that's an additional sanity check that our diversity metric measures something meaningful. And the upper bound is any token has the same probability. And so uniform probability of tokens, what is the diversity of that? That is the number that comes out. Those are the lower and upper bounds. And we basically show that with respect to those bounds, how diverse the data sets are or aren't. So data sets are 3 to 5 times more diverse than the lower bound, or half as high as the highest diversity. Does that sort of make sense? That is more or less 0.4 goes to 0.24. That is where this numberage comes from. And in reverse, these. Yeah. Does that make sense? Yes.
Is it surprising that the error bars are so small?
I think that error bars are, yeah. I think I would have to look at this detail, but I think we had a lot of batches. I think 600 or something. And when you plug it into the confidence interval formula, like Z of P times standard deviation divided by square root of N, I think that ends up being like it just divides it by a lot, especially because the sigma is already bounded by 1, I think. So maybe that's why. So I guess maybe it is expected. And you can control that number with the how many batches you get. The more batches you get, square root increase. And yeah, the accuracy.
Can you use this metric to try to reduce the size of a data set while maintaining sort of a similarly high diversity? And that way, like, ideally, like, your training is not that affected, but you're just training on less data.
So is that with respect to like how the model's performance will do, or is that really? Yeah, so I guess like that is like a separate question. Right now, I'm just showing that the diversity of the data sets we're using to train models is high, and defending or explaining that the diversity metric is valid because all the previous slides explained that the diversity metric behaves the way we would want it, and it also behaves with respect to these 2 sanity checks. So I haven't talked about anything yet about how it affects downstream performance, but it is, I do have one slide about that. Yeah, some preliminary experiments. Great question. Actually, that is the next slide. So, okay, the next slide is preliminary experiment. So we pre-trained from scratch GPT-2, 51.5 million, that's the number of parameters it has, on datasets with different diversities. And the question is, does pre-training on more diverse data causes better evaluation loss on datasets that are diverse, that measure general intelligence? Because maybe like, if you only have like a specific data task that you care about, training on general data, if it doesn't already include it, won't really help. So we try to have sort of like, if you have a diverse data, have that diverse evaluation task. That is what we're approximately trying to do. We're trying to control as many things as we can. So approximately the same number of tokens, and training conditions are as similar as possible. The model is the same, right? If we change the model, that would be confusing. And we see that as the diversity increased, the cross entropy decreased on both of them, on both evaluation tasks. So yeah, that is our current experimental results. And it has lots of limitations, but yeah.
How does the diversity compute on which model? Because you need to have an embedding.
Yeah, so like this is, so like, you fix some sort of model to compute the diversity. GPT-2, a pre-trained GPT-2, Llama, whatever, a random one, as long as all these three diversities are the same model is used, then you have like the same embedding. So like the model being trained and the model being used for creating embeddings is separate. They're separate things.
And how do you know that like the order of diversity, they invariant with the embedding?
Do you mean like if we
Like, so
change
for
the
example, like you have a bunch of sanity check, it's probably corresponding to
yeah
one underlying pre-trained model. Does do you have like
Yeah.
confidence to say if I
Yeah.
just change?
that is an
that
interesting
underlying-
question. I don't think I've done it. I think I have actually tried to compute the diversity coefficient with much larger models, like 7 billion llama, but 7 billion llama is quite large, so it's not very easy to compute anything with 7 billion llama.
Oh, yeah, I
Yeah.
I just find a little counterintuitive as the diversity depending on another model. So diversity is like a measurement of data and it
Yeah.
depends on the model.
Yeah, I don't know. I think like lots of people find this confusion, and honestly, it puzzles me. But I'll try to empathize as much as I can and explain how I think about it. But like, you need to represent the data always. If you choose the identity function, you're representing the data. So I don't know how you go around not having a model. You always have a model.
Right.
Yeah. So why don't we choose a model that captures as the best semantics we can? The reason to use like a random model, in my opinion, is that you don't have to pre-train to get a good embedding. And if everything, all the sanity checks I did pass for random models, then that makes everything more computationally efficient. Because the thing that diversity, I hope it only needs is that the model that you use is consistent. That is like the hope. But that is an experiment I haven't done. We did the experiments that were the most consistent with previous work first. Yeah, we do have some computations on random models, but we didn't, it was just sort of to compare how the diversities would compare in absolute values to these. But
No, I'm
yeah.
not suggesting like a random model or not like a model at all. I have to say the existence of a model in this metric is interesting.
Yeah,
You
Yeah.
happen to know like or like happen to have like a prediction if you have better underlying embedding model, if the diversity become more accurate?
yeah, I think I would have to think about that. I think I've definitely thought about this question and have notes on it. I think overall, the more important point is that you always need you're always doing a model, whether you're choosing to call it a neural net or not. Like other metrics, other diversity metrics use kernels. I don't know how to get around the model thing. Like you're always doing a model, even if you use the identity function as like the main point you're trying to make. Yeah, I don't know if that helps.
I mean, there could be like a non-parametric definition of diversity that like some ranking, something that does not really depend on like fitting a function or taking the gradient with respect to parameters.
Oh, is that what you mean, Sam? Yeah, I don't know.
Yeah,
Like a
it
kernel
just felt
function.
like it just felt like it's learned something then like if you learn something already,
Yeah.
the task like somehow
Yeah.
it might become
Yeah.
easier than it might seem to
Yeah.
the model that have not
Let's talk
learned
about it
something.
offline. But I think my hypothesis is that answering your question, how does a model help or not? If the model, I would hope that the more accurate the model is, the better diversity. The diversity is more accurate. I would hope that would be my prediction. Perhaps I'm wrong, and all you need is like a fixed model for non-parametric or parametric or some fixed way to compute the diversity, and maybe that's all you need. But that is not something I know.
Can I ask just one more question?
Yes,
like a
yes.
burning question.
Yeah.
So I really interested in like data selection.
Yeah.
And I always have this like need of like reducing my data set into some like sufficiently diverse data set. I have, let's say, a huge one, and now I want to use your metric to make it more manageable. Perhaps
Yeah.
I don't have that much computing. So what is the implication? Like like how do I choose a subset? Like would this facilitate that?
I think it could, and that is something I'm trying to do. That is why I came up with like the data alignment. I guess like this is related to your question. How do you select data? The current experiment I want to do is you have a target task, you have a set of batches or data examples, and you compute the task to vec distance between your target and all your data examples, and then you sort it, you choose your top K. Then that is like a way to select data. But maybe there's like more smart ways to select your data. But the point is now that we have distances, maybe we can choose which data points to choose more carefully. And this slide is sort of showing that as the data aligns more, it seems that the loss goes down, which is sort of like nice to know. I know that it's 304, so I can go in more detail, but at the very least, you saw this slide.
Yeah,
And then I guess I had more things. And the conclusion, just to conclude, the diversity coefficient sort of behaves as expected. So therefore, it's a valid metric for diversity. At least that's what we're trying to argue. And current NLP data sets are objectively high. And maybe one more bullet point, preliminary data suggests that more alignment improves accuracy and more diversity improves evaluation loss on diverse evaluation data sets. Yeah, and that's everything. Thank you. Thank you for your time, everyone.
Okay, we'll push other questions offline. Thanks for folks online. I think we'll end the meeting here. Thanks, everyone.